The central limit theorem is huge, and we start to see why the normal distribution is so important to us. So let's say we have this spinner, and let's say every place on this spinner is equally likely to be spun. Maybe it's computer generated. And so it looks like our probability of spinning a 10 is about 0.6, this is about 0.3, and this is about 0.1. So let's go with that. If we look at a probability distribution, we have this right here. And then let's find the expected value of x, which is the mean of x. And if you recall, what we do is we take every value that a random variable can take on, multiply it by its corresponding probability, and then add all of this together. Oops, that's a 50 times 0.1. When we add all this up, we get 18.5. So even though it's impossible to spin an 18.5 on any one spin, on average, we expect to get 18.5 points per time that we spin. Then the variance of x, now we can find this using list 1 and list 2 and do one variable stats. But it's good if we can understand that, hey, no problem. All we have to do is take the deviations of each score, how far it is away from the mean, and square it, and then multiply that by its weight. So we find our standard deviation by doing similar things to what we did before. Take 25 minus the average, the mean average, square that deviation to get rid of the negatives. This is multiplied by its weight of 0.3. Then lastly, we take the 50 minus the mean. We square that deviation and we multiply that by 0.1. Add all those up, we get our variance. Take the square root of that to get our standard deviation. Our standard deviation is going to be 1.609. All right, so we have our expected value and our standard deviation. Well, let's look at this on a number line. The results that we're going to get when we spin, we're going to get 10s more often than not, and then 25s and the occasional 50. So that's going to be what's happening, and the mean average is right here at 18.5. If this is 0, 10, 20, 18.5, there's our mean average right there. Now let's think about this for a moment. What happens is if we start spinning, we could get a 10, maybe a 25, maybe a couple more 10s, maybe a 50, maybe a 25, maybe a few 10s in a row, another 25, another couple 10s, a 50, and 25. Well, pretty soon if we take a lot of these spins together and we add those values up and we divide by our sample size, then where should those means of those samples be distributed? By golly, they should be in here. We should be getting X bars sample means that are really close to the 18.5. And what we're going to find is they tend to be normally distributed. So even though the population is discrete, there's only 3 numbers you can get when you spin this spinner. If you take a sufficiently large sample, usually a sample of at least 30, then you know if you take your 30 spins randomly selected, add them up and divide by 30 to get a sample mean, and you could get sample mean after sample mean, all the same sizes, then those sample means should be approximately normally distributed, even though the population's discrete to begin with. So, what does that mean? Well, let's suppose we said, all right, I want to know, what if we took a sample, what if we took an SRS or we spun this thing 60 times? What's the probability that the mean score that we get on this spinner would exceed 20? Now we know on average we're supposed to get 18.5, so for us to be lucky enough to get a sample mean above 20 from 60 spins, well, we'd have to be pretty lucky. So how lucky? How do we answer a question like that? We know this has a probability of 0.6 and this is 0.3 and that's 0.1, but how do you find the probability that a sample mean would be greater than 20 from 60 spins? I'm glad you asked. What we're going to do is we're going to go to the central limit theorem. And the central limit theorem says that sample means will be approximately normally distributed regardless of the shape or type of probability distribution whenever the sample size is at least 30. And the mean of the sample means will be the mean of the population, whatever the random variable's mean is. And the standard deviation of sample means will be the original standard deviation divided by the square root of the sample size. So when we do this problem right here, we realize, oh, well, you know what? The sample mean, or I'm sorry, the population mean is going to be at 18.5. That's going to be right here. And the standard deviation is going to be that 1.609 that we had before, and we're going to divide it by the square root of 60. And so we're going to get a distribution of sample means that's going to be in here like this. And to answer this probably, what's probably the x bar is greater than 20? We're going to say, well, let's see what the probability is that we get above 20, because a sampling distribution is theoretically how the sample mean should be distributed due to random chance. We're going to spin this spinner and it's all up to chance as to the numbers we get, but maybe we get lucky and we get a lot of those bigger numbers, the 25s and the 50s, pulling our sample mean up. So how likely is it to get a sample mean above 20? Well, we just do normal CDF or use z-scores, and what we would find is we get a probability of 0.1756. So about 17.5% of the time, if you take a sample of size 60, you can expect to get a sample mean that is above 20. Now, how about this? How about we do this? If you recall back in the tree problem that we were doing from the sampling distribution video, we looked at daily tree sale revenues for Christmas trees off a lot being normally distributed with this mean and this standard deviation. We could take small sample sizes, like we took a sample of size 7 only, and we knew that the means of those tree revenues would also be normally distributed. But what we know now is that the Central Limit Theorem says, regardless of the shape or type of a probability distribution, even if it's not normal, like the spinner thing, it's discrete, only 3 possible outcomes, that is not normal. It's not continuous, it's not bell-shaped. But you take a big enough sample size of at least 30, and your sample means are going to be approximately normally distributed, you can use z-scores and normal CDF to find your probabilities. So what we have here then is we say, okay, we can know our standard deviation for our distribution, and even if we have something like this, let's suppose we're looking at daily behavior of values of certain stocks, or maybe one stock, I don't know. But the mean average is 24 1/8, that's per share, the value of that stock, but it fluctuates with this standard deviation. However, it's not normally distributed. It's a little skewed to the left. It's kind of multimodal. It's kind of bizarre. And we'd like to know something like, all right, what's the probability that after 30 days, what's the probability that our mean value for those 30 days would exceed $25 a share? Okay, so we're looking at the mean value from a sample of size 30. Now it should be noted that it wouldn't be right to take 30 consecutive days, 1 month, because that would not be a random sample. Those days would be dependent on one another, so officially you're not supposed to do that. We got to pretend or theoreticize that we would take 30 days at random, and they could be from any time period. So we're fudging a little bit there. But here we go. What's the probability that after 30 days the mean value of the stock would be $25? Well, what we have to understand is, even though these are the scores or the values of the stock 1 day at a time, all right, these values right here, if you randomly select 30 of them, and they could come from just about anywhere, but you added them up and you divided by 30, then you would tend to get a distribution of those means that would be normally distributed. And so even though the population is multimodal, because you take a sample of size 30, the central limit theorem kicks in. The central limit, the limit of the center, it's approaching the mean. That's why it's called the central limit theorem, the center being the mean. And so it's normally distributed. Now all we have to do is say, oh, okay, let's find the probability that our mean would exceed $25. That's up here somewhere. And we'd find that probability right there. So what do we need to do? Well, we know that the mean of the sample means is still going to be the 24 1/8, but we have to change the standard deviation of the sample means from the standard deviation of the stocks 1 day at a time to that of a mean of size 30. So we would have to take this bugger and divide it by 30. This would give us a standard deviation of 0.606. So about 61 cents is how much the fluctuation would be, how much the standard deviation would be for sample means, for taking 30 days at random, adding them up, getting a mean average. This is the standard deviation for how much those sample means should fluctuate due to chance. So what do we do now? We use this mean and that standard deviation in this sampling distribution, and we say what's the probability of exceeding $25. So again, normal CDF, type in 25 and a big number with that mean and that standard deviation, and you would get 0.074. So about 7.5% of the time, when you take 30 days at random from this population, you would expect a mean value for the stock to be $25 or more. That's how the central limit ties in to sampling distributions of means, and this is enormous in life. You take samples of size 30, you don't even care what the original distribution was. You can use z-scores and find probabilities that means will exceed certain things. And this is the gateway to inferential statistics, the stuff that we're going to be covering soon, that really is how we test things out and how businesses or scientists can know how unusual their particular mean was and how to apply the scientific method with probabilities of being right or wrong to help test hypotheses or conjectures that we make. So this is big time stuff.